Okay, so we have solved 11 and 12. I'm going to leave some of the questions alone. I provided the answers already, and some of the questions are conceptual questions, so that is on you. So let's continue with the last 2 or 3 questions. Calculate the radius of an iridium atom given that iridium has an FCC crystal structure and a density of 22.4 grams per centimeter cube. Atomic weight is 192.2. So we simply use our regular theoretical density expression here. What was that? N times A divided by Avogadro's constant times volume of the unit cell. For FCC structures, what do we know? We know that if we draw the structure again, 8 corner atoms, 1/8 of them are inside. Then there are 6 face atoms, half of them are inside. In total 4 atoms. So 4 atoms, 192.2 grams per mole, divided by Avogadro's number. Let's say atoms per mole, and volume of the unit cell, which is for FCC the edge of here, the face diagonal is where the atoms touch each other, so a square root 2 is 4r. Then this is going to be 2 square root 2r cubed, and that is equal to 22.4 grams per centimeter cube. This is given to us in the problem. Okay, so this is simply an algebraic equation now. 2 square root 2r cubed is going to be equal to 4 times 192.2 divided by 6.022 times 10 to the power 23 times 22.4. Take cubic roots of both sides, then solve for r to get 0.13606 times 10 to the power minus 7 centimeters, which is 0.136 approximately nanometers. Okay, so that was that. So the rest of the questions are again somewhat conceptual, mostly conceptual. So question 20. 2 previously undeformed specimens of the same metal are to be plastically deformed by reducing their cross-sectional area. One has a circular one, other has a rectangular one, and dimensions are given here. Shapes of the cross-sections are kept constant, only dimensions change. Which of these specimens will be the hardest after plastic deformation? So this is related with percent cold work of the specimen. So percent cold work is defined as, can be defined as, for example, percent reduction in area. So what is percent reduction in area? Percent reduction in area is defined as initial area minus final area divided by initial area times 100. Okay, so for the first specimen, the circular specimen, what do we have? The initial area is pi times 15.2 squared divided by 4. It's the diameter. And the final area is pi times 11.4 squared divided by 4. Take the difference, divide to A0. So when you substitute these expressions, you will see that pi over 4's cancel out. So 15.2 squared minus 11.4 squared divided by 15.2 squared times 100. That's going to be your cold work for the circular specimen. That turns out to be, I think, something like 40%, 43.75%. Now move on to the rectangular specimen. For the rectangular specimen, dimensions are given directly. 125 times 175 minus 75 times 200 divided by 125 times 175. Now times 100, this whole thing. That turns out to be 31.43%. So compare these values. Circular has higher percent cold work. If you increase the amount of cold work on something, that's going to cause an increase in the dislocation density. Dislocation density increase will mean that dislocations will be harder to move. So we expect that increase in, for example, the yield strength, the ultimate tensile strength, which in turn causes an increase in the hardness. So circular specimen will be harder than the rectangular specimen. So that kind of explains question 21. For simple cubic, body-centered cubic and face-centered cubic crystal structures, what is the relation between lattice parameter A and atomic radius R? What is the number of atoms in a unit cell? For many times we have shown these relations. For simple cubic, the lattice parameter is 2R, since atoms are touching along the edge of the unit cell. And number of atoms is 8 times 1 over 8, which is 1. For body-centered cubic, if you draw the structure again, there is one atom sitting at the center of the body, and the atoms are touching along the face diagonal, so a square root 3 is going to be equal to 4R. Number of atoms in a unit cell, 8 corner atoms, one atom sitting at the center, that's going to be 2 atoms. Finally, for FCC, what do we know? The atoms are touching along the face diagonal, so a square root 2 is 4R, and there are 8 corner atoms plus 6 face atoms. That's going to be 1 plus 3, and that concludes recitation 1.